So, hi everyone, I'm Sarah O'Flanagan, obviously not Rob, he's not here today. So I'm pleased to welcome Dr. Marc Joanisse. He's a professor at Western, where he's a member of the psychology department, as well as the Brain and Mind Institute. He received his PhD from the University of Southern California, and his research examines the neurocognitive bases of language and reading, focusing on developmental language disability and reading disorders in children, second language learning in adults, and processing of complex words. This laboratory uses a multimodal approach, including eye tracking, EEG and event-related potentials, functional MRI, and diffusion-weighted MRI. He serves on the editorial board at the Canadian Journal of Experimental Psychology, and has previously served as an associate editor of the Journal of Speech, Language, and Hearing Research, and on the editorial board at the Cognition. He's currently associate chair of graduate studies in psychology at Western, and is also the chair of Canada's Tri-Council Panel for Responsible Cognitive Research. Welcome, we're pleased to have you.
Thanks, Sarah. It's nice to see you all, and it's really nice to be here. As I was saying before, I haven't been to these rounds since we did them over on Highbury Street, so I think that probably dates me going back a decade at this point. But I think that's where I first met Rob, and so it's nice to be back. And I'm going to talk about some of the brain imaging and behavioral work we've been doing on reading developing kids at Western and with the kids at the Thames Valley Board and other schools. I'm on a short leash because my connector is weird. But so if I walk back and forth, I'll try to keep my head turned this way. So we're going to talk about reading ability and the idea that even though kids learn to talk in an effortless way, then in a way that seems to be acquired in an incidental fashion, so that all you have to really do is talk around the child for them to start to figure out what the structure of spoken language is. Learning to read was different. Teaching children to read really is an act of teaching them how to read this written code. And it's because of the nature of that modality and the fact that when you're reading, what you're doing is you're mapping a new code, which is a visual code of language, a written code, onto what you already know, which is a spoken code. And the two are not actually the same, right? They don't look, one looks like something and the other one sounds like something. Another way to think about it is that humans didn't really evolve to read. That evolutionarily speaking, humans evolved to speak, evolved to have some sort of spoken language. And yet, the written form is something that's a relatively new innovation that's only 3,000 to 5,000 years old. So for many tens of thousands of years, we had humanity and presumably spoken language, and yet written language has only popped up relatively recently. And what it means is that the way that the brain wires itself for spoken language is going to probably be slightly different than the way the brain wires itself for written language. And so even though my lab studies both of those things, here what I'm going to talk about is written language and some of the interesting things that go into teaching kids how to read and what happens when reading breaks down. If we think about what the process of reading is, we can think about it as having two channels or two sorts of mental operations that go into it. So if you get a perfectly nice word like professor here, we have a conceptual knowledge of what professor means. So when you see this word on a page, one could imagine that what you're doing is you're seeing that word that's a familiar word that you've seen before and mapping that onto a mental representation of what a professor is, right? So if I can, this person here. The other thing, though, is what we know about words isn't just the meanings of words. We also know the sounds of words, and we call that the phonology of words, which is how the individual sounds work together to give you that word. So you could also think about reading as an act of translating a written code onto a phonological or spoken code. That written code and that phonological code are not the same thing. The phonological code is sequences of articulations that produce sounds in the air, whereas the written code is the letters that go with it. And as I'll show in a few minutes, the letters don't map perfectly onto the sounds. So one way to think about it is that English has something like 35 to 40 phonemes, individual sounds that we can make. And yet we only have, what, 26 letters. So already there's a disjunction between the sounds in the air and the written letters on the page, that we're having to do various tricks to get you other kinds of sounds written out in longhand. Another way to think about that is there are only 5 written vowels, and yet most English speakers produce either 10 or 11 different individual vowel sounds. Okay, so there's a lot of different ways in which you can spell out vowels, for instance, doubling them and so on, that allow you to spell out vowels that we don't actively individually produce as distinct phonemes. The point here, though, is the idea that there's maybe 2 modes of reading, 2 ways of actually reading words on a page, and it has to do with linking up the letters on a page with either the whole word semantic knowledge of that word or the phonological code, the sounds of it. So we can think about that as a whole word approach versus a decoding approach, where a whole word means you're taking, you're recognizing a word holistically. So you've seen the word before as an entire chunk and recognize it for what it is because it's a familiar word. We can sometimes call that a whole word or a direct word of reading. And then we can also think about reading as happening analytically, where individual letters are recognized for what they are as mapping onto individual phonemes that you know. So for instance, if you got the word shoot here, you know the SH letters when put together produce the sh sound. The two O's together usually make the oo sound, and the T typically makes the t sound. So you've got sh, oo, t. And here again, this disjunction between what reading is and what spoken language is really being apparent, right? We've got 1, 2, 3, 4, 5 letters that actually produce only 3 phonemes, sh, oo, and t. So right there, it's kind of a challenging translation act between the letters on a page and the sounds. And we think about this analytic process. Sometimes we'll call this analytic process, is that on this slide? Yeah. Sometimes we'll call this analytic process a decomposition process, or phonics, or the sublexical route. And it depends on who you are, right? So if you're in a faculty of education, you might call it phonics or decomposition. If you're in a cognitive psychology lab, you'll call it the sublexical route. These are all just different ways of repackaging the idea that when you're reading a word, you can think about the individual phonemes that make up that word, rather than just recognizing the word for what it is wholesale. In new readers, that is in kids who are learning to read, often we're emphasizing learning to read through this process that we'll call decoding, this process in which you are learning how the letters go with different sounds. And the reason is that that becomes incredibly useful, right? So if you want to know what sound goes with the letter B, you think about the letters, the words that have the letter B in it, like black, grape, bone, and book, and think about what the first sound of those words are. I'll start with the B sound. And that allows you to associate that letter with that sound so that the next time you see a new word that has that letter in it, you can make a pretty good guess that that's going to start with the B sound. And that works even for words that end in that B letter, right? So rob and club both end in the B sound and both end in the letter B. And likewise in the middle, a word like ability, stable. So it's generally regular. Although we say, well, yeah, there are some exceptions, right? So for instance, the first B in the letter bomb is B, but the last B isn't actually produced, right? We don't say bomb, we say bomb. It's a silent B. So it's an irregular domain. But you'll notice that it's still fairly regular enough that you don't, bomb isn't pronounced lork, right? You're still producing the B, the O, and the M the way it's spelled out. So even English words that have irregular spellings still abide by this decomposition process to a certain extent. It still remains a fairly useful way to learn how to read. So I can say, well, that's good and fine for kids, but what about adults, right? People, if you ask them to make a judgment about what's going on when they read a familiar word, they're going to swear up and down, no, I'm not doing this thinking about the letters that go with the sounds thing, I'm just recognizing that word. I know the word bomb, so I'm going to read bomb. But in fact, this decoding process is incredibly useful. We do use it all the time. For instance, new words come into the language all the time, like Furby, Internet, Google, Blogosphere. You can tell this slide is about 10 years old, and that, yeah, those were new words. So I've actually updated today. So now we've got new words like botnet, CRISPR, microaggression, and heel work. These are all words that have entered the Oxford Dictionary just in the last couple of years. So new words come along all the time. So heel work is what you do with the dog. You're training a dog to walk on a slack leash. Microaggression is when you're being rude to somebody in a way that's not overtly aggressive, but still puts them down based on gender, race, and again, in a psychology department, I hear all about it because it's a big topic in social science.
You only get to see your macro.
That's right. So we do get new words all the time, right? And you want to be able to read those words, right? The first time you see botnet, it's not like, oh, I don't know what that word is. You may not know what a botnet is until you start reading the New York Times. But the way that it's sounded out is something that you're actually able to use. Another way to think about this is there's actually considerable evidence from cognitive psychology experiments that adults are using this phonological decoding process all the time, even though they swear up and down they're not doing it. So I'm not going to talk about any of this today, but you can do things like visual priming, eye tracking, brain imaging studies, where you show very clearly that people are activating a phonological code, even for words that they know very, very well. These effects are very rapid and they're very unconscious. They don't involve sitting there and moving your lips as you're reading. Okay, so it's a really quick, rapid, unconscious process in which you're engaging phonological knowledge really rapidly. So the way that kids learn to read through this phonological route, and I'll argue why I think that's the case in this slide, is something that we carry forward with us. We don't give up on it later on in life. We continue to use that phonological information. Doesn't mean we don't also use full word processes. It's clearly some balance between the two. So as I said, readers will swear up and down that they're not decoding, in spite of evidence being very clear that they're actually doing so. I've had many arguments on the internet. So if we go back to learning to read, though, the other piece of information here is that what we know about learning to read can be really strongly informed by cognitive psychology research. There are different techniques in teaching to read that are going to emphasize one way to read versus another. That is a more decoding versus a whole word approach. And indeed, this decoding or phonics approach is very heavily referred often when we're talking about reading remediation and early word learning, where it's the idea that kids are being taught to sound it out. It's the old-fashioned way of learning to read. It's the way that I think most of us learn to read in this room, and is seen as being kind of slow and laborious and frankly a little bit on the boring side, because what you're doing is reading very boring short words that all tend to have the same letter patterns in order to get your mind used to seeing those letters going together and making sounds. Whole language has been another approach that suggests that kids should learn words, not sounds. And that what they should be doing is recognize the entire word all at once, and also emphasizing that it happened in this incidental learning kind of way. So in the 80s, it came along as this fun and new science-based approach of teaching kids how to read, which focused on learning individual words and de-emphasizing any kind of use of spelling sound cues as being old-fashioned and really stranding kids who weren't able to put the time in to learn those letter sound correspondence. And indeed, that gave rise to this whole language debate in which phonics was cast, especially in the 80s and early 90s, as this very boring way of teaching kids to read. It was extremely old-fashioned, wasn't science-based, and often involved reading simplistic texts, right? Dick and Jane books that are just not that exciting to read. Versus the whole language way that was sought to cut out the middleman, where here the middleman is phonology, where what you're doing is you see the word and you activate the word in your head, you just learn it. And the idea was that you would teach kids to read these interesting texts via memorization and repetition. So they got these very interesting texts and were basically taught to read it over and over again, usually by reciting it out loud in front of the class. And it was often with an emphasis on memorizing texts as a way of learning the words. And the idea there was that you're going to teach kids how to learn to read like adults. And indeed, we saw wholesale changes in reading policy in places like Ontario and California in the 1980s and the 1990s that really turned out to be major disasters. Okay, so California and Ontario, so I trained in California and then I moved to Ontario. Both those places turned out, I had nothing to do with it, I'm just saying, but it did seem like there was a real dip in reading scores in kids who learned to read in the 1990s that really wasn't turned around demonstrably when places like, when the entire Ontario curriculum moved very strongly back towards phonics-based and phonological awareness training-based approaches, to the point where it's actually gone in the other direction, where you get these kids who actually make the normative tables in our standardized scores be completely out of whack. It's extremely difficult to find kids who score down at the first or second percentile anymore because of how much of an emphasis we've seen on this phonics phonological awareness approach. And we've had to come up with new normative tables to really define what the bottom end looks like as a result of that. Math, unfortunately, is going in the other direction. And so we are seeing a lot of issues in the other direction with how math is taught. I think it's basically the literature that's about 20 years behind the reading literature, but catching up quickly. If anybody who's talked to Daniel and Sarah knows, they're catching up quickly. In any case, I like to think about this as in the past, but it does seem to be the case that a lot of the way that reading is taught carries the vestiges of the whole language approach and still is not perfectly ideal. There's still lots of places that emphasize what they'll call a mixed approach, or balanced reading, or reading recovery. All of these have turned into secret code for places where they still emphasize a lot of whole language approaches.
Marc, when you said that they did whole word because it was scientific,
Yeah.
What was the science?
The basis of the science was that they were teaching kids to read the way that people like Noam Chomsky as linguists in the 1960s decided kids learned to talk, which is through incidental exposure to language. And so this guy named Steve Krashen, who also was a USC prof, who I never actually met when I was a graduate student there, really emphasized this idea that linguists had taught us how children learn to speak, and that you could use those lessons from linguistics to also translate over to reading. It was scientific in the sense that it had this theoretical basis in science, but it wasn't scientific in the sense that he actually ran the experiment. Instead, he just convinced people to adopt this approach, which sometimes is the way that educational policy is set, right? Whoever yells loudest or has the flashiest demonstration on that PE day is what wins out. Okay, so that's my advertisement for educational policy and how kids learn to read. But it segues now into what I'll talk about for just the next part of the talk, the last part of the talk really, which is what we study in my lab, which looks at the relationship between reading failure and where reading is in the brain. And so one question that comes up a lot is people say, well, where's the brain's reading region, right? Where can we point to on this little picture for a magazine article that we're writing that says, this is where your child's brain is developing through reading? And of course, then I read this side and say, of course, the answer is much more complicated. So if you take the results of any random neuroimaging study where you present people with visual words while they line an MRI scanner and see what lights up, as it were, what you see, in fact, is that a whole swath of regions in the left hemisphere are activated for reading, regardless of what you're doing, but also that depending on what we call reading, you're going to get different parts of the brain lighting up. That is, in this experiment, this is with adults. We got adults to either read for sound, so they were making a judgment about whether two words that they saw sounded like. That's what I lit up here in yellow. And then the other color, somehow this turned my red into gray, but the other one is red. Stuff in red here is reading for meaning, where they looked at two words and decided whether one of those words was the name of an animal. So they're making a meaning judgment rather than a sound judgment. And what you see is that those two give overlapping but not perfectly overlapping brain maps, that you get slightly different parts of the brain letting in for both of those kinds of processes, depending on whether you're making a judgment about the sound of a word versus the meaning. But in general, it looks like it's a whole swath of the left hemisphere, and if I turn this brain around, you'll see some of the right hemisphere as well. A lot of brain regions seem to be important to read. Stanislas Dehaene has suggested that we should think about this as a reading map. He wasn't the first person to come up with this idea, but I borrowed this slide from him. And so the idea is that we've got this occipital lobe that's getting visual inputs, and the entire visual world comes into our cortex through the occipital lobe. And then it gets passed along to regions, for instance, in the ventral temporal lobe, including this special region here that we'll call the visual word form area, which seems to be very interested not just in any kind of random visual stimuli, but letters organized into words. So he calls this a visual word form area. And it's the idea that when you organize letters into meaningful words, this region seems to be particularly active. And it acts as kind of a way station where there's nothing about the meaning or the sound of the words that's stored here, but it does seem like the visual forms of individual words then gets passed along to other parts of the temporal lobe and the parietal lobe, having to do with accessing the meanings of words, and also the other regions having to do with accessing the sounds of words. And in fact, these regions here look a lot like the brain's spoken language network as well. So it does seem like we've got this visual system that's slapping itself onto spoken language system, so that in order to recognize written language, what we're doing is first doing a visual processing, a broad set of visual processes, and then passing that along to spoken codes having to do with the meanings and the sounds of words. Importantly, though, these are all interconnected brain regions. Okay, so there's lots of little circles and lots of arrows here. So it turns out that all of these little pieces of this reading network all matter. That together they work to create this this whole greater than the sum of its parts thing that we call visual word recognition. In terms of reading disability, you can look at different parts of this brain's reading network and see what's going on in kids with reading disability. And so, for instance, you can, when I say reading disability here, what I mean is what we commonly call dyslexia. So I'm going to use those two terms interchangeably. I use the term reading disability because I think the term dyslexia makes it sound like a medical diagnosis, and also suggests that there's a really firm phenotype of kids that we'll call having dyslexia that are separate from kids who have typical reading or who may just be generic readers. I don't think that distinction is real, and we can talk about that later on. But in general, I think reading disability captures the idea that this is a distribution of abilities where these kids are at the bottom end of that distribution. The general definition of reading disability here is that these are kids who have a deficit in reading development. So we define dyslexia based on the ground truth of our observation that poor reading is what defines poor readers. It's no more complex than that. So these are kids with slow and laborious reading. So that is, when they are reading, they read very, very slowly. They produce many errors as they go along, both in terms of how they sound out individual words, and also in terms of reading entire sentences. They also show poor comprehension of text, probably related to the fact that when you're reading very, very slowly, what happens is your ability to maintain what's in the context of a sentence or a text is going to start to fall off, right? If you can read through a sentence very quickly, you're going to be able to hold it and understand it much better than if you read through this. I don't think the comprehension deficits that we see in reading impaired kids goes any farther than that. There are some kids who also have other kinds of language deficits having to do with comprehension, with semantics, for instance, and they're going to show reading problems as well, having more to do with poor comprehension. That's not really the kind of reading impairment we're talking about, and I would suggest that in those cases, their reading deficit is secondary to a broader language deficit. Importantly, these kids are typically described as having normal cognitive achievement. There again, I think there are some pitfalls in the sense that I don't want to exclude kids with intellectual disability, even though most learning disability approaches assume that kids with learning disability are only going to be defined as such if they have normal intellectual. I think that we probably need a more inclusive approach, and in my lab, we don't exclude kids based on low IQ. We measure their IQ to keep it under consideration. What happens when you take kids who come in with reading deficits and exclude the ones who fall too far off the scale for low IQ, you still end up with a group of reading disabled kids with low IQ relative to the control kids. Okay, there's some comorbidities there with lower cognitive achievement and lower reading achievement, especially as you get older, because a lot of the learning that happens through reading. So and that's both verbal and nonverbal learning as well. So I think excluding kids solely on the basis of low IQ and saying they're not allowed to have a learning disability probably isn't going to fit with the way that we've been seeing reading disability play out in the cognitive psychology literature.
What do you call low IQ?
Pardon me?
What do you define as low IQ?
Anything below, say, standard score of 85 on a non-verbal composite. That would be a typical thing. And so in the past, when we've excluded kids based on low IQ, we use that standard score of 85 on a couple of non-verbal measures. And again, I mean, I think in the educational psychology setting, it's very, very different. And the school psychologists take a very different view of it, in part because I think they want to move kids with lower intellectual achievement off to other kinds of services. But the kinds of reading remediation approaches that we know work with kids with reading disability don't work differently in kids with low IQ. They work just as effective. And so from our standpoint, it really makes sense to be as inclusive as possible. The other thing to know here is that in common parlance, when you talk about dyslexia, you'll often hear people talk about kids who are reading backwards, or seeing letters upside down, or confusing left and right, and so on. That turns out to not be highly diagnostic of reading disability. It turns out that all kids, as they learn to read, confuse letters and confuse, for instance, D's and D's, and write words backwards because they forget which way the words are written. When we see kids with low reading ability, you'll see that that stage of development where they tend to reverse letters is somewhat protracted because they're slower to learn to read. But it's not typical of reading disability, and it's certainly not diagnostic, right? So, for instance, I've got my example here. Here's my daughter Marianne, who wrote her name in chalk on the sidewalk perfectly backwards, including getting the A backwards, where she just completely forgot which way was right and left. You'll notice she got the R. Somehow she got the A backwards and the E. No, but the E was okay, but the R is facing the right way. Okay. Literally, the next day comes home from school is a worksheet where she'd written her name properly. And so what happens is it's just a normal developmental stage of reading development where kids forget which way is left and right. And I've got a little Christmas ornament that I made for myself in kindergarten that my mom kept where it's really cramped. So these are charming. Sometimes I tell that joke in class and students like I literally anyway, so what does cause reading disability if it's not kids seeing stuff backwards? Well, the argument, the prevailing wisdom here is that these are children with difficulty with phonology. That is, with difficulty with spoken phonology as well as using phonology to read. And so the idea there is that people have come up with relatively sensitive measures of spoken phonological processing that doesn't involve reading words, where kids with reading disability do also seem to fall behind. So it means that reading disability isn't specific to reading, that it's some sort of pre-existing difficulty with the sounds in your head that are making it difficult to map the written form of language onto that spoken language code. Oh yeah, there we go. So we'll often talk about this in terms of phonological awareness. So phonological awareness is often talked about in the context of reading, but in fact it's spoken language tests. So it's tests like, say, split without the p. So what's split without the p? Split, right? So what you're doing there is you're taking a word, which is split, thinking about what the sounds make up split, and taking that p sound out and putting it all back together. So you're manipulating phonemes in your head. Kids with dyslexia or reading disability have tremendous difficulty with that kind of test because it involves thinking about a word as made up of individual discrete phonological units, which turns out to be really difficult. Likewise, rhyming tests. So candle and sandal. So do candle and sandal rhyme? And thinking about the spelling here doesn't help you, right? Because I've cleverly given you an example here where they do in fact rhyme, but the spelling is different. So there again, spoken language is, rhyming is a spoken phenomenon that has to do with special units of analysis in words. We have to think about what those units of analysis sound like and compare two words. Again, kids, 5-, 6-year-old child at risk for reading disability would find that task especially. The reason why we think phonology matters, well, it's because the idea that a phonological deficit in how you organize the phonemes in your head is going to impair learning spelling to sound correspondence. If the idea is that you're trying to figure out how that letter on the page maps onto the sound bone in your head, then learning that association is going to be impaired if that phonological representation, that sound representation is impaired. So the argument is that these kids have perfectly normal visual representations. So you can see the words on the page fine, they can process their acuity for visual information is reasonably good. And that what's wrong here is mapping that visual representation onto the auditory representation. It's going to express itself in particular with reading novel words. So if I come up with these non-words like CRISPR that you've never seen before, an individual with reading disability finds that especially with poor learning to read. And yet they're okay sometimes, especially as they go on with reading familiar words. But when they encounter novel words that we've just made up, and we have standardized tests that involve reading non-words on a sheet of paper, they find that especially difficult. We may see compensation, especially as kids progress and especially as they get with reading via this direct route by recognizing the whole words. So there they may be learning to read either through self-teaching or by being just exposed to reading and being told through tutoring to recognize entire familiar words. You remember, recognizing familiar words is not going to be useful for nonsense words that you've never seen. Okay, some of the work that my lab does then is trying to map that idea. What's wrong with, what's wrong cognitively in reading impaired kids onto what's going on in their brains. And so for the rest of the talk, I'm going to talk about functional MRI and also diffusion tensor imaging, which is another kind of MRI, where we're taking what we know about the behavior of these kids and trying to go deeper into what their neural organization looks like. And as I'll get to later, also maybe what reorganization could look like as a function of remediation. This is probably nothing new to folks, but we do see it, we use MRI scanners not just to take static images of anatomy, which is our friend Homer on the left, but we can also take dynamic images to look at function. So the idea is that it's the difference between a stable photograph and a video, where a video is a moving image of things happening, right? It's many pictures taken one after the other. And so functional MRI is simply taking many MRI images one after the other every 2 or 3 seconds, and in a way that actually is optimized for looking at hemoglobin in the blood, so that as neurons take up more and more glucose and oxygen in order to do more work, the hemoglobin level in the blood capillary bed around those neurons shows a decrease or an increase as a function of the cognitive tasks. So we can actually localize then where in the brain something is happening based on those metabolic changes that occur when we're using neurons more, when those neurons are working harder. And indeed, we've done various functional MRI studies on kids with reading disability. So for instance, here's a study that we did with typical readers versus reading impaired children aged 9 to 13. This is something we did about 15 years ago, where we looked at brain activity while kids are matching that spoken word that they heard onto a picture art that they saw on the video screen for them. And here I'm looking at the right hemisphere. The reason is that a lot of what we know about reading suggests that the left hemisphere is particularly engaged during reading. And yet, and so as a result, we don't see a whole lot of brain regions lighting up in the right hemisphere. Whereas kids with reading disability show a whole lot of activity, especially around this phonological region of superior and middle temporal gyrus, that seems to be an unexpected set of activity. We see just as much activity in the left hemisphere in both groups, but the dyslexic kids with reading impaired kids are the ones who show lots of right hemisphere activity as well. So if we subtract those two, what we see is, in fact, again, a pathological hyperactivation of the right hemisphere, even during a spoken language test. So the kids weren't actually being asked to read anything here, but instead they were making a phonological judgment where they saw a picture and they had to think about what the sound that goes with that picture is. So these were very easy pictures, like things like lock or fan, and then they heard the word fan and decided yes or no is that the word that goes with the picture on the screen. So very straightforward spoken language processing. So that's a typical kind of experiment we can do there. This is replicating what other people have found in the written domain, where you seem to find overactivation of temporal regions in the right hemisphere for kids with reading disability. They seem to be allocating more right hemisphere resources to this task than typically developing kids, even when it's a spoken task and not a written task. One of the things that bugs me about functional MRI is that differences in functional MRI activation are going to tend to track behavioral differences, right? Things that are going to be easier versus more difficult to do are going to have some sort of neural activity correlate that goes along with it. So my attitude is often, well, should we be surprised that poor readers show differences in their brain activity while they're doing a reading test, or even when they're doing a non-reading test like a spoken language test that we know very closely matches their reading ability? What would be really cool is if we just put somebody in a scanner and take a picture of their brain and just, have them lie there and think for a little while, and then figure out what's different about their brain, even when they're just thinking. Because then it's less closely tied to an exact task. Another way to put it is, what if I chose the wrong task? Would I have found a difference between the kids with dyslexia and the kids without dyslexia? Maybe not, right? And then the question is, well, maybe you just used the wrong task. Whereas I say, oh, look, their brain's normal. So it's very difficult to know whether you're ever using the right task. One approach here is to take a task-free approach to functional MRI called resting state functional connectivity, where let you do exactly what I said, which is an individual lies in the scanner as still as they can for about 5 minutes, usually either with their eyes open, staring at a little fixation cross, or you can have their eyes shut. Often if you get them to shut their eyes, they'll fall asleep. So we like to have them stay eyes open and awake and alert. But we tell them just let your mind wander. So they don't get any special instructions. They're not being told to do anything in particular. But what happens is that naturally, as you lie there, your brain starts to activate, either due to conscious flow of thought or even unconscious processes that just happen. And an interesting thing occurs where you can see brain activity amongst many different brain regions start to just spontaneous brain activity go up and down as a result of this, as measured by this functional MRI signal. So somebody had the clever idea that you could then take the functional MRI signal in different parts of the brain and correlate them with each other. So that with 5 minutes of activity, you can look at the rise and fall of activity in those regions. And interestingly, certain parts of the brain tend to co-activate very actively with each other. They form these interesting networks of brain regions where, as one brain region's activation goes up, the other brain region's activation. So that's what I've tried to model out here, right? That, for instance, regions A and B seem to correlate with each other, and A and C correlate with each other, but regions B and C don't correlate with each other quite as much. So you can come up with these maps of functional activity that are simply telling you naturally how interconnected these brain regions are. So what we did here was we took 58 kids who we recruited from London, Ontario community. So some of them were recruited at school, some were just recruited through advertising. And we had them do 30 minutes of MRI scanning, during which they did about 6 minutes of this resting state scan. So in addition to some other scanning paradigms that I won't talk about today, we had them just lie quietly while we measured the spontaneous neural activation. 58 of those kids, about 60 of them had a genuine reading disability that had been diagnosed through the school board. A handful of others were reading impaired, just as we had identified them in the lab. They just were part of that distribution of poor readers that just comes into the lab sometimes. And the rest of them were weak to average readers. They were ages 8 to 11 years old. And we also got them to do various behavioral tests out of the scan. So the idea was that in addition to getting the brain scan, we would also test their reading abilities in various ways, their math abilities in different ways, as well as other things like nonverbal IQ measurement and a few other behavioral tests as well. So the idea is they came in on the first day, did about an hour-long battery of behavioral tests. We also practiced scanning, so we have a fake scanner, we call it a zero-T scanner, or a sham scanner, where they practice line still and get feedback about whether they're lying still properly. And then, as long as they enjoyed that, they come in the next day and actually get scanned. This was all done by Alex Cross, who's over there on the left, who's a combined program in health sciences PhD student in my lab. So she's training to be both a speech pathologist and a PhD in a combined 5-year program. So Alex and I have been working on this for about the last year and a half. What you see is that when you take the brain's reading network that I showed you a few slides back, and just look at those different brain regions, which I've shown here, you can look at the connections between those using this resting state connectivity, and what you find is that these brain regions do tend to talk to each other. That is, they do tend, as activity goes up in one region, it tends to go up in other regions. And the way that we know that is that there are statistical correlations amongst various subregions of this reading network. What you can also do, though, is look at how the connectivity of that network is modulated by performance on a behavioral test that you acquire outside the scan. And there it starts looking a little bit more like magic, where you look at the connectivity in each individual child's network, and then you correlate that level of connectivity with, for instance, how they scored on a measure of nonverbal reading. So this is the Tower test of nonverbal reading, where kids over 45 seconds have to read as many nonsense words as they can on a page. And it's standardized so we can correct for age. And it looks like these are all positive correlations, where the kids who scored higher on that Tower test also showed higher correlation levels, but only in certain subregions of this reading. And in particular, it seemed to have a lot to do with left and right thalamus, and how those subcortical regions are communicating with left hemisphere regions like supplementary motor area, fusiform gyrus, and so on, that are cortical brain regions that we know are important to reading ability. It also seems like the strongest effect is for nonverbal reading. When we look at the same test, or if you look at a comprehension test where the child reads a text and has to, we measure how quickly they read the text and their ability to comprehend those texts. Reading impaired kids find those difficult as well, but the correlations within this reading network are much weaker. So it seems like the reason why we get poor readers showing different patterns than typical readers is not the same for comprehension as for this nonverbal reading. And likewise, on the math test, we see other connections mattering for a math test than what we see for those reading tests. So different sub-connections within this reading network seem to matter for different kinds of learning, and seem to map onto different kinds of behavioral tests that we require on the scanner, suggesting that the reason why you're poor at one aspect of reading might not be the reason why you're poor at another aspect of reading. And then the same is true also, we've done it also for things like nonverbal IQ, and for different subtests of math. So overall, this resting state fMRI technique gives us some interesting insights, because it doesn't ask kids to actually do anything, right? They just have to lie there and quietly have their brain scanned. And what we're looking at is what the structure of their brain's reading network looks like dynamically as they're simply lying quietly. And it does seem like there's a non-trivial relationship between that reading network and their behavior outside the scanner on these important tests, scholastic achievement and reading achievement. That is, different reading subskills seem to map onto different kinds of cognitive. It also doesn't seem to be just a proxy of IQ or math achievement. That is, we ran other behavioral tests like IQ that I illustrated today and math achievement to suggest that it's not just that some kids fall behind in everything and they show suppressed activity patterns and suppressed connectivity patterns. It really seems to be specific to reading. I'm going to skip ahead. No. So if I look ahead here, the other thing we'll say is that these same kids are enrolled in a longitudinal study where we're now collecting the second half of that longitudinal study, where the kids with reading impairment are also receiving Empower Reading, which is an approach to reading remediation that's currently being tried out at the Thames Valley District School Board. So these were kids enrolled in special congregated classrooms where they get Empower instruction several times a week. And so what we're doing is scanning them twice, both before and after. So they're getting rescanned on a 1-year follow-up, and we're looking at how we can track improvement based on that second scan. And also, I think very interestingly, the possibility that we could maybe try to predict improvement as well. That is, before they actually start with Empower Reading, they got that first round of scans. Can we predict how well they're going to respond to the Empower Reading intervention based on what their brain looked like at that time on scan? So that's another way of thinking about it in terms of prognosticating based on time 1, not just looking at changes from time 1 to time 2 in terms of how the brain's reading network changes over time. I'm pretty much out of time, right? Do I have a few more minutes?
Oh, yeah.
I have a little bit more data here, also looking at white matter connectivity, so maybe I can give you a flavor for that. If you look at how the brain, these cortical regions that I was talking about in the brain's reading network, how they communicate with each other, they communicate with each other through white matter fibers in the brain, where white matter is these myelinated axons of neurons that can be connected across fairly distant brain regions and allow them to all communicate with each other, rather than simply neurons being right next to each other being the ones that do all communicate with each other. So you can use something called diffusion tensor imaging to take static images of the brain's white matter. And using this diffusion tensor imaging, or DTI, you can figure out what the microstructure of that white matter is like and make guesses as to the efficiency of connections along those white matter tracts. I'm going to skip a few slides here. What we can show is, no, I'm going to skip that. Sorry. So what we've done was we've used diffusion tensor imaging to take these static images of the same kids who were in that first study. This is a subset of kids from that first study. And look at white matter tracts, especially ones that we know are related to left hemisphere and right hemisphere language processing, and figure out whether the structure of those tracts, that is, how efficient those tracts are, can tell us something about what their behavior is inside the scanner with regard to reading. So this is 24 kids, so it's 14 kids who are reading disabled who are getting the Empower Reading intervention. 10 kids who were just typical controls, so they were weak to typical readers who were not identified as having reading impairment. And they were again ages 8 to 11 years. All of them are first language English speakers.
Attention on class, code white, Pratt to south, lane way 4. Code white, Pratt to south, lane way 4.
We're good? Okay. Some of them are left-handed, 2 of them were left-handed, the rest were right-handed. Again, we don't exclude kids from our studies for being left-handed. Again, because we assume that being left-handed is not going to preclude you from having a reading skill. Scanned as before using our 3T scanner at the Roberts Institute, and some various DTI sequence vagaries here. Basically, it's a 5-minute scan with a child as still as possible. If you've ever had a DTI scan, it's kind of a funny sensation because the whole scanner kind of wiggles in funny directions. What it's doing is pushing all the protons in your body in one direction or another and figuring out how effectively they're able to move in those different directions to figure out how water is diffusing in your brain. The idea is that water diffuses in your brain differently if it's in white matter than if it's in gray matter. Apparently, it doesn't hurt these kids.
Attention on class, code white, all clear. Code white, all clear.
We looked at a whole bunch of tracks. I'm only going to talk about 2 tracks, one in the left hemisphere, one in the right hemisphere. That's because that's where the action was. But there are other tracks where not much is going on. The left Arc Fasciculus, you might remember from taking undergraduate, if you did any kind of undergraduate work on language in the brain, is famously a white hemisphere region, a left hemisphere white matter tract that connects the classical Wernicke's area down here in the temporal lobe, to the classical Broca's area up here in the frontal lobe. Got a little animation here because I had a few extra minutes yesterday, just to give you an idea of where it is in the 3 dimensions. So it's a 3-dimensional structure of white matter that connects those regions. And so that's what Arc Fasciculus looks like. What you can do is take Arc Fasciculus and look at the white matter in each individual child and figure out, is there something about the structure of that Arc Fasciculus that might map onto the behavioral measures that we acquired outside the scanner. And indeed, it does look like that. What I've done here is I've taken that Arc Fasciculus and I've overlaid a statistical map where I've correlated the fractional anisotropy, which is just a measure of white matter diffusivity, onto their non-word reading ability. So here, a blue color means that there's a positive correlation between how well structured the white matter is and how good a non-word reading is. And it does look like their Arc Fasciculus does capture some of the variability in their non-word reading ability. So you can also, so this is the same image again, so that's for non-word decoding. You can also look at cipher reading, which is reading words that are familiar words, and it does look like this argument also has something to do with reading familiar words as well, where better readers show better FA, which is fractional anisotropy, compared to poor readers. And then as a control task here, I'm just including a math test. This is Woodcock-Johnson 3 calculations, just to show that this is, again, a proxy of general scholastic achievement or general ability or their ability to stay awake while we're testing. And it's not that at all. It really has very specifically to do with reading, and we think in particular non-word reading. You can also look at right hemisphere. Here we're looking at the right inferior longitudinal fasciculus. So this is running along the ventral stream of the temporal lobe, connects visual areas to semantic and phonological areas along that ventral stream. And so that's, I want to show my pretty animation. And so there again, it's just in the right hemisphere, it's a bundle of white matter fibers, and is giving us an idea here that subtends pretty much the entire length of the temporal. If we look at the microstructure there, what we see is actually the opposite. We see a positive correlation between this, a negative correlation between the anisotropy and the behavioral tests as acquired outside the scanner in terms of phonological decoding. What that means is that kids who are worse at phonological decoding actually show better microstructure of that right hemisphere tract, almost as if they're overusing that right hemisphere tract in general, which is what differentiates them from their typical reading peers. Again, it looks like this is reading specific. You give them, if you look at reading, if you look at a sight word reading task, you see a smaller effect, but it's still there, colored in red. If you look at calculations, you see no effect at all. There doesn't seem to be any relationship with scores or other non-reading related scores. So it looks like what we see is an interesting trade-off here between the left hemisphere, where better readers show better left hemisphere white matter microstructure, and poor readers who show weaker right hemisphere microstructure. So there's a balancing act between those two. So having higher microstructure is good, but it may actually be an index of some sort of difficulty with how the left hemisphere is organizing itself and a reliance on the right hemisphere as a compensatory mechanism. So quickly summing up then, we do see that there's static white matter conductivity measured with DTI does seem to map onto different sub-abilities having to do with reading, both positively and negatively, suggesting some sort of atypical reliance on the right hemisphere with reading disability. Again, looking ahead, these kids are all getting remediation. We're interested in whether we can predict their response to remediation based on these measures that I just showed you, and also whether white matter changes as a result of remediation, whether teaching kids to read through this phonics-based approach called Untitled Reading is going to change that white matter microstructure in ways that make them look more like typical readers, or possibly show that they're circumventing what typical readers are using and using other channels instead. We don't know yet, but maybe in a year's time we'll have some clear answers on it. So yeah, finally this alphabet pays off, right? If I can quickly wrap up here, what we've talked about is the idea that building reads critically on phonological knowledge. That phonology is super important for learning to read. We're starting to understand how this maps onto different brain structures in a more fine-grained way. And particularly this idea of network connectivity. It's not just individual parts of the brain in isolation, but rather how different parts of the brain talk to each other. This seems to really matter. This idea of reading disability, it looks like it's a specific problem with decoding in phonology. And we're starting to isolate the brain signatures of this atypical functional anatomical connectivity, functional connectivity, which is fMRI, and anatomical. So let me thank my co-authors here, in particular Alex over here, who did a lot of the hard work on the brain imaging part of it. I've got a lovely lab over at Western. You're welcome to come visit us anytime. And the donors that paid for this national research. And I'll thank you all for your time.
Thank you very much. That was excellent. I'm going to open it up to questions.
I have an obvious question.
Yeah.
So the deaf kids struggle notoriously to learn to read, and it makes sense because they're not having any of that phonological decoding experience or opportunities, they can't hear it. However, there are some deaf kids who do become accomplished readers, and I'm never sure how they do it. So I've got to keep, I've got a ton of questions. Yeah. But have you ever looked at deaf kids with fMRIs in terms of this kind of data?
No, I hope to get to it eventually, and we did do some stuff with behaviorally with deaf kids and reading. And unfortunately, the grad student who worked with me on this ended up leaving. So I mean, it's something I'm curious about because we still really don't know, right? Are they activating the phonological code somehow?
Well, it makes sense that they would because language is mapped in the same area of the brain in deaf kids as it is in hearing kids.
Yeah.
We used to think it wasn't. We used to think it was more right hemisphere based, and now we know it is mapped very similarly. Right. But how are they accessing that? It's
pretty mysterious. I mean, a lot of what we know is from bilingual, bimodal individuals where you get them to look at sign and you get them to hear speech and you find commonalities. And there, obviously, they have access to phonology, so it could make sense. But then there are these individuals who are profoundly deaf who also seem to show the same effects. And there, it's always bewildered me.
Yeah.
Because you can also see things like phonological priming in those, right? Where they seem to be activating very rapidly the phonological code of a word so that when they see another word, they can make a very rapid judgment about the word based solely on what we think of as the sound of the word. But obviously it's something more profound.
So maybe it's time for you and I to collaborate again.
You gotta start thinking about it. I know. I think it'd be really interesting. I mean, there's some work from San Diego coming out about this, and it's just.
Yeah, and there's some like all the dads in Washington.
Yes.
There's a reading lab there, but I'm not so sure that they've actually looked at this from this perspective.
There's a recent work by Karen Emery at UC San Diego. Yeah. And I think her work is as close as it's getting right now, but not really from a, they don't think about it as a reading test. They think about it as, well, they're English visually, they're learning visual English. They don't think of them as readers. They don't think about the reading process in the way that the classic word nerd like me cares about, where we're thinking about decoding and thinking about the cognitive operations that go into this sublexical knowledge. So I think there's an opening there, for sure. Leo.
Marc, when you were talking about the functional and the anatomical, so I didn't get to connect those parts. You showed different regions activation, but then you go and you show two different tracks.
Yes.
So how do you try to put these things together? How do you try to see the?
Not yet is the answer. So those two literatures, usually what happens is you're a DTI lab or you're an fMRI lab or an EEG lab, and I just try to do everything. But it does put me on the spot because then I got to learn how to connect them. And the issue with some of the attempts at trying to get the DTI data to line up with the functional connectivity literature is we don't always know when we see a DTI tract what the gray matter regions really are that are responsible for that white matter difference. So I think we've got to start looking at really tying those two together, and that's the next step with our data. Is we've got data sets on both, and in some cases it's the same kids, and try to merge them together. So I think it's got to go in that direction, right? It doesn't make sense to me why you would see a functional connectivity difference, but not see a white matter connectivity difference. But sometimes you do, and I'm not sure why, right? I mean, isn't the idea that that function is getting communicated across white matter? But I think there's still a lot that we don't understand about white matter connectivity, especially about what its relationship to functional connectivity is. A lot of the good work right now is in mice, right? It's because I think they've got a better way of mapping neural substrates in these things in mice. And
So in that step, where are things at?
I think that we're still at a step where the best data come from behavioral studies and from controlled studies of intervention, rather than trying to rely too heavily on it. So I'm working with a team from Sick Kids that's doing Empower Reading.
Yes.
It's Maureen Lovett's lab, and they do this very, very well, and they run random controlled trials with their interventions. And I think they're very convincingly showing that certain kinds of approaches really are superior to teaching kids to read, especially reading impaired kids. But they're curious about the fMRI stuff as much because it's sort of interesting and flashy as anything else. I don't think we've still figured out exactly whether it's going to tell us any novel insights about outcomes that we couldn't have figured out behavior. One thing that I'm curious about, that I'm hopeful about, is there is this whole class of reading impaired kids who are very slow responders. And we don't know why they're slow to respond, why they're treatment resistant, and whether there are neural reasons why they might be treatment resistant, where with a big enough sample of kids in our study here, maybe in tandem with some other work that's happening that's very similar at Georgia State University, we might be able to figure out why some kids are treatment resistant, right? It's not just that they start off as poor readers, but no matter how hard you try with intervention, they don't seem to get better. Those are the real, those are the difficult ones, because then you're wondering, well, is it the approach wrong? Would a different approach work better? And it may be that there are neural signatures where you might be able to see that in kids early enough to figure it out. So that may be where it is, because right now they all look the same, they're just poor readers. And if there's a cognitive test that tells us how those treatment-resistant kids look different from the non-resistant kids, we haven't figured it out.
And can you describe a little bit about the Empower program?
It's largely phonics-based early on, but it's a multi-stage thing where they start off with emphasizing learning letter-sound correspondences, and also letter-sound correspondences that aren't just how each individual letter goes to each individual sound, but how sequences of letters work together, so that, for instance, the E at the end of the word changes the sound of vowel, and how to think about that in terms of letter-sound correspondence. As it goes on, though, there's also an important component to it, which is reading comprehension, where it's especially the Empower program for middle schoolers and high schoolers. It really emphasizes how to comprehend a text, not just understand a sentence, and how to construct a way of comprehending an entire text, so that kids who are being asked to not just learn to read, but read to learn, are given those tools to progress through school and be better at all those aspects. So it's a very good program. It's supposed to be a 2-year program. The Thames Valley Board right now is rolling it out for grades 4, 5, and 6 as a 1-year program, just the first end of it as a phonics-based program. As time goes on, I think the idea is to move it forward with a later intervention part, but I think their hope is they can get to kids earlier on and run it as a 1-year program. It's also, though, that it's run in the classroom. It's not a one-on-one tutoring situation. So it would be effective in a classroom, even in a classroom where there's all kinds of reading abilities, from the best to the worst readers. You could work with all kids at once. It wouldn't leave some kids behind. Whereas other programs that really emphasize one-on-one, so Linda Newell, for instance, and what Gilligan approaches, are really one-on-one tutoring intensive, and which is great if you've got the resources to bring the child out for multiple hours a week. I think where Empower is trying to make some headway there is to create a classroom situation where you're able to teach kids how to read in a classroom setting that's really focused on reading, that happens multiple times a week, but that's in a group setting.
So what would your opinion about what's going on in Jolly Phonics?
I haven't really looked at it. I think Jolly Phonics is also classroom-based, right?
Yes, yes.
And I think what's happened there is, for one reason or another, the Thames Valley Board is moving more towards empowerment. I'm not sure why. I know that right now the Jolly Phonics, at least the last time I looked at it, which was a while ago, it was school by school, and certain principals got really interested in and implemented. The board, I don't think Thames Valley Board all in.
It's also new for children. I mean, they're starting in SK.
Right. Right.
As opposed to what you're talking about empowerment.
Right. Well, I think earlier is going to be better for
Yes.
sure. And there again, they what they do right, I think, is that all the kids in JK, SK get a phonological awareness screener.
Yes.
And so you know how to identify those kids, but it's how you act on it, right? And I think it's going to depend on the teacher, and it's going to depend on the resource teacher. And I think we've got good contacts with the resource teachers, and they seem to understand now. Because 10, 15 years ago, when I started doing this at Western, I spoke to people in communication sciences, and none of them studied, and it just wasn't on the map as a reading, as because they're communication sciences, that's obviously speech, so they weren't doing reading, and I think that's switched. A lot of there's a lot of interest in reading, right? Clinical psychologists and psychologists, learning impairment. In fact, of education, you get the impression that they're just taking a completely different view of learning disability, and seeing it as learning disability rather than reading. And then with speech, so I think things have moved in the right direction, and I think that's the thing.
I just wondered if you did any of your studies on anyone with hyper?
No, not yet. One thing we did was we looked at, this was an honors thesis project, because we had screened absolutely everybody we could. We actually did go back and not just look at the kids who were poor readers, but also the kids who were very, very high end readers, and tried to figure out what was going on in those individuals. And from our standpoint, what we looked at it was what the different environmental variables might be to create a poor reader versus a good reader. And it does seem like socioeconomic status is one of the things that creates poor readers, or that puts kids at risk for reading failure. Socioeconomic status doesn't seem to put you at risk for being a really great reader. We're still not sure what happens there. It seems to be that being in a school or being from a neighborhood that's socioeconomically better off can move you from that bottom quartile into the middle of the distribution, but it doesn't seem to move kids from the middle of the distribution to the top of the distribution. Those kids just seem to be off on their own, right? We're not sure why, and they're everywhere. They're in the very poor reading schools and the very high reading schools. So we know which schools are poor reading schools. We know where to find reading impaired kids, but the really super readers are everywhere. We don't know. I mean, unless the kids have comorbidities.
So we also see kids who are really good decoders
Mm-hmm.
who don't understand some of the autism, some of them
Yes.
don't. So I'd be very interested to see your studies on those, because presumably one of your little circles is missing, but
Yeah, for
I've
sure.
always wondered how that could be, because some of them are quite impressive.
But then when it comes to text level or
But in
sentence
terms of their
level,
understanding,
Yes.
but they can just motor through the
Yeah.
But the other problem is a lot of those who are very good readers like that, deserve to code, and their comprehension is good for reading, they are horrible spellers,
mm-hmm.
right? And again, a lot of schools don't teach spelling anymore.
Right.
And you think, well, if they're that great of a reader, why can't they spell?
Right.
Right? But they don't spell.
Yeah, that does puzzle me. And I have my oldest daughter is a terrible speller, and I've never understood what they're teaching. Right? And it works in one direction, but not the other somehow. You can
And so-
recognize it, how it's spelled,
Right.
but when it comes to actually generating the spelling, it doesn't work in the other
Yeah.
direction.
And that's why word predict is wonderful, right?
Uh-huh.
Because they immediately recognize it from the list of the word is, but they still can't sit there and spell it.
It's kind of fallen off the curriculum,
Yeah.
for sure, right? And I think part of it is a message that, spelling doesn't matter as much.
Well, it is, that's,
Right, and so don't fuss over spelling, whereas, when I was a kid, I fussed over spelling. It was-
well, I figure technology solves the problem.
Yeah, that's right, autocorrect. Should I just blame autocorrect?
Yes, it comes up with interesting things sometimes, doesn't it?
Yeah.
And before you read it, press the button, it's gone up, and go, no, what have I done now? Okay.
Are there any differences in the corpus callosum in kids who have more activation of the right hemisphere?
We haven't looked at it. We looked at it in adults and did find one corpus callosum difference in poor versus good reading adults, and that's work that I did with Suzanne Welcome about 5 years ago, where we did find one specific subregion of corpus callosum that seems to be what connects auditory cortex in the left hemisphere and the right hemisphere. And so two phonologically related regions talking to each other over the corpus callosum does seem to correlate very closely with how well those individuals were, again, at decoding, but not their comprehension ability. So I think we yet to look at it, but this one is it's a different analysis pipeline, so we'll have to run it through that.
There's so many more things to ask.
I know. Well, it's a good problem to have. I mean, I've got another 20 years to go here, so I need to keep busy.
And does handedness correlate? I know you said earlier you don't.
Just not enough left-handers to see really anything. If you look at those studies, right, it's about half of left-handers have right hemisphere instead of left hemisphere language, so, it would have been 1/5. So,
But that's not what they did in the epilepsy program. They said that 10% of people who were left-handed had atypical language. It's actually a lot rarer to have atypical language development.
so it's smaller than that.
Yeah, if you talk to like Sue Brand and Bella over at UB, they'd be able to really talk about that, but that's really important, obviously, if you're having surgery for epilepsy to get that place right.
Absolutely. And what are they doing there? Are they doing fMRI to do the pre-surgical mapping?
Sometimes.
Yeah.
But the fMRI scanner was down for quite a bit. So what they were using was the Hughes words that they had with during Kira from.
Oh, with the dichotic listening?
Yeah.
Yeah, right.
So, and that was apparently quite good. And then if you had patients who had atypical development, they'd go on to do sodium amytal or etomidate.
Yeah. Oh, interesting.
This is kind of a question in a way, but when people learn Chinese, right, they don't learn so they don't use an alphabet. They practically have to assign this. So it's what you were explaining as some sort of holistic kind of stuff. What is dyslexia or these disorders? What is the incidence of those things in China and Chinese speakers?
So one of the things about Chinese is that Chinese actually has phonological cues within words that don't get talked about, but are there. And indeed, kids who have reading disability in China have difficulty with reading, in particular with those kinds of words that contain phonological cues in those full word representations. And if you use fMRI and look at the brain reading network in people learning Chinese versus learning English versus learning Spanish, what you see is that the same regions seem to be affected by dyslexia in all those cases, and seem to be showing the same activity in typical readers in people who don't have reading. So there's a lot more commonality than there are differences. It's probably an equilibrium between phonological and whole word processes where Chinese emphasizes whole word more, but it doesn't totally upset the balance where they're only doing whole word. And so there have been a few interesting papers coming out that seem to suggest there's more common than and the incidence.
It might have mapped onto the sign.
Well,
Right?
that's exactly what I just
Yeah.
said. Maybe we need to look into some Chinese deaf kids.
Yeah.
I think we need a lot of money to do that.
Well, but
But that
there's
makes perfect
1.2
sense.
billion people in China. So the pool of subjects is much
Yeah.
bigger.
Time for a field trip.
Yeah.
But is there a different type of dyslexia then in people trying to do Chinese?
The argument is no. The argument is that its neurological bases are the same, that the brain signatures that you see that we call brain signatures of dyslexia in English-speaking kids are the same signatures that you see in the Spanish kids, in the Italian kids. I think in the study that I'm thinking of, they ran it in Beijing, New Haven, Connecticut, where was it in Spain? Oh, in like San Sebastian, Spain, and in Israel. So it was 4 different writing systems, or 3 different writing systems, 4 different languages, all different, what you call depth of orthography, different holistic versus decoding emphases, and they all show the same signatures.
So that kind of explains the depth part too, that it's a language communication or like visual, like recognizing a symbol or a gesture or whatever.
The brain just
Using the
wants to
same
use
parts
those
of the brain.
channels, right? Those are just what it uses.
Thank
Fantastic.
you
Well,
again.
Thank you very much.
Please sign it.
You can just leave the evaluation straight down the alphabet. Thank you.